Welcome everybody. My name is Kathrin Lorenz from the Max Planck Institute for Human Cognitive and Brain Sciences in Leipzig, Germany. I'm happy to present our recent paper to you, which is entitled Characterization of Pseudo-Continuous ASL, Simulations and Experimental Validation. The labeling scheme in Pseudo-Continuous ASL consists of a train of short RF pulses of the length tau p and the interpulse delay delta tau p. The pulses are applied in the presence of a labeling gradient, Gmax, with a successive rephasing gradient in the interpulse delay. The flip angle, the interpulse delay, and the moment of the rephasing gradient are chosen so that the averages of both the B1 field and the gradient correspond to that of continuous ASL. The control condition is realized by adding a 180-degree phase to every other RF pulse. Regarding the gradient scheme, two types of the control condition are possible. In the unbalanced mode, which is shown here, the gradients of the control differ from that of the labeling condition, indicated by the orange area, so that positive and negative lobes of the gradient are equal and the average gradient becomes zero. The unbalanced mode is recommended in the ASL white paper because it's less sensitive to off-resonance effects. By contrast, in the balanced mode of P-Castle, the gradient schemes of control and labeling conditions are identical. That means the average gradient is still different from zero. The balanced mode enables vessel-encoded P-Castle to investigate arterial territories. It has the additional advantage of being more robust against hardware imperfections. The main issues of the present work are which quantities, besides the average B1 and the average gradient, are important for P-Castle, and can balanced P-Castle be made insensitive to off-resonance effects? To study this, we did simulations based on the Bloch equations. We applied the kinetic Bloch matrix recursively and run simulations separately for both the labeling and the control condition. This example, without consideration of T2 relaxation, shows the trajectories of the magnetization MZ in both conditions, the labeling condition in orange and the control condition in black. The magnetization starts from the equilibrium value M0 at the position far below the inversion zone and travels through it with the velocity of arterial blood under the influence of P-Castle. The simulation is finally stopped if the change of MZ is smaller than the millionth part of M0. The result is an inversion in the labeling condition, but no inversion in the control condition. From the Z magnetization values, efficiency measures are derived: the inversion efficiency, alpha L, and the efficiency of the control condition, alpha C. Please keep in mind that alpha C is zero for an ideal experiment. The labeling efficiency is then calculated by the difference of both efficiency measures. The first important result is the major influence of the RF duty cycle, DRF, on the effective labeling efficiency alpha. DRF is defined as the ratio of the pulse duration and the interpulse delay. Here you see contour plots of the three efficiency measures in the columns for three different duty cycles in rows. A contour plot illustrates the respective efficiency as a function of average gradient and average B1. A rapid increase of alpha C beyond a certain average gradient value is observed, which strongly depends on the duty cycle. For lower duty cycles, this edge shifts towards lower average gradients and thus limits the suitable G-average range to get sufficiently high alpha values. However, for DRF of 50%, alpha C exhibits no significant dependence on G-average. Thus, the resulting conditions are similar to to the unbalanced Pseudo-Continuous mode. Furthermore, the very same behavior can be seen for other interpulse intervals. Here an example for a delta tau p of 1.8 milliseconds is shown. This reveals that DRF has a higher impact on the labeling efficiency than delta tau p. The second important quantity is the labeling gradient Gmax, which has a similar effect on alpha C as the RF duty cycle. The example here shows the results for Gmax between 9 and 4.5 millitesla per meter. The edge in alpha C is shifted towards lower G average values when Gmax is reduced. The reason for the analogous influence of DRF and Gmax is that the angle between the effective magnetic field and the z-axis is influenced similarly by both. Imagine there would be an additional intrinsic magnetic field gradient, which shifts the actual G average in the first row from 0.4 to 0.6 millitesla per meter. Alpha would be diminished from 85 to about 50%. On the other hand, if the range of suitable G average values is broader, this would not affect the efficiency value, as can be seen in the bottom row. Based on these findings, we developed a strategy for optimizing balanced Pseudo-Continuous experiments. We determined a range of gradient values, delta G, centered at G center, for which the labeling efficiency is always higher than a desired minimum value. We achieve independence from the intrinsic field gradient when delta G is larger than twice the magnitude of this gradient. In our study, we derived optimum parameters for a maximum field gradient that was observed in vivo at 3 Tesla. That's why we request a delta G of 0.4 millitesla per meter for our analyses. What we define as the optimum is a measuring point with the lowest average B1 possible and the corresponding G center, where the highest alpha min is achieved under the constraint of delta G of 0.4 millitesla per meter. In the table, examples of such operating points are shown. The first 3 rows demonstrate that with a high DRF and a high Gmax, a value of minimum alpha of about 90% is obtained. For the last 2 rows, where DRF or DRF and Gmax are lowered, respectively, alpha min drops. Note that the second row refers to a simulation of unbalanced Pseudo-Continuous with DRF of 50% and Gmax of 10 millitesla per meter, as recommended in the ASL white paper. For verification of the simulation results, we performed single-slice EPI measurements to obtain labeling efficiency values in the human internal carotid artery. The EPI readout was carried out at the base of the cerebellum, with the labeling plane 1.5 cm below. Quasi-continuous labeling was done within a short repetition time of 150 milliseconds. Thereby, 3 different signals were acquired sequentially: the signal in equilibrium, in the control, and in the labeling condition. And the labeling efficiency measures were calculated from these quantities. Further, we performed an error estimation for the obtained efficiency measures using a short TR ASL model, which considers relaxation and the mixing of signal contributions during blood transport. With this fast measurement protocol, we were able to run multiple experiments to scan the average B1 average gradient plane with 2 different duty cycles in one session: a low duty cycle of 27.8% and a high duty cycle of 55.5%. At the right-hand side, you see the comparisons between simulated and experimental contour lines for the low at the top and the high duty cycle at the bottom. The characteristic features of all 3 efficiency measures could be reproduced, especially the edge of alpha C at the low DRF and the independence from G average at high DRF. It leads to a broad plateau of high alpha values, see at the bottom, whereas to a tiny G-average range with higher alpha values, see at the top. The comparison between simulations and experiments shows an underestimation of experimental alpha values of 4 to 8% due to blood transport effects. However, they agree quite well with the predictions of the short TR ASL model. In summary, we have shown that the labeling gradient Gmax and the RF duty cycle DRF are the most important quantities for the performance of the control condition in balanced p-castle. We found that with the Gmax of at least 9 millitesla per meter and DRF not smaller than 50%, balanced and unbalanced p-castle become comparably effective. For perfusion measurements at 3 Tesla, a labeling efficiency of about 90%, independently of magnetic field gradients, is predicted by our simulations. And experimental verification of this prediction was achieved in vivo by a fast single-slice EPI readout. Thank you for your interest in this presentation. For more details on the theory and the methods, please see our original paper. Thank you very much.